Section 1110 is about the Taylor-Maclaurin series. So start off with f of x equals a power series, the sum from n equals 0 to infinity. And then we have c sub n x minus a to the n. That's our basic definition for a power series. So if you think about that, if you put in 0, you have c sub 0, which is a constant, and then x minus a to the 0 power is the number 1, so that's just a constant, plus c sub 1, x minus a to the first, plus c sub 2, x minus a to the second, plus c sub 3, x minus a to the third, plus c sub n, x minus a to the n, plus, and it keeps going to infinity. So then let's look at the first derivative, just like we did in the last section. So we're going to say f prime of x equals, well, the derivative of c sub 0 is, that's a constant, so it's 0, so it's gone. So the derivative of c sub 1, x minus a to the first, is just the constant c sub 1. Because then the derivative of x minus a is the derivative of just x, which is 1. Plus, we're going to take this 2 and bring it down. We have 2 times c sub 2, x minus a to the second. I'm sorry, that becomes to the first. Take 1 away. Plus 3 times c sub 3, x minus a to the second, plus, now if we look at this one out here, we have n times c sub n, we have x minus a to the n minus 1, plus ... infinite series. So now let's look at the second derivative. The derivative of this constant is 0. The derivative here, we still have 2c2, but the derivative of x minus a is 1, so this became our constant. Plus, and I'm going to write it this way on purpose, but we have 3 times 2 times c sub 3, x minus a to the first, plus ... plus, we have n times n minus 1 following the same pattern, c sub n, x minus a to the n minus 1 is n minus 2, and so forth. Let's look at the third derivative. What happens to the first derivative each time? The derivative of this constant is now 0. So then this will be our first term. So we have 3 times 2 times c sub 3, x minus a to the first, and the derivative of that is just 1. So we say plus n times n minus 1 times n minus 2, c sub n, x minus a to the n minus 3, plus so forth. Are you following these derivatives? We're going to go 1, 2, skip a few, so we're going to skip down. Let's look at the nth derivative of f. So the nth derivative, this is a constant. Everything leading up to it is a constant. This went away on the this first term went away on the fourth derivative, and the next one went away on the fifth derivative. So on the nth derivative, we get here and we have n times n minus 1 times n minus 2 times n minus 3, all the way down to 3 times 2 times c sub n. And here we'll have x minus a to the n minus n because it's our nth derivative, plus other terms. Now notice these other terms all have x minus a, the sum power. So keep that in mind. So as we look at this, notice all of these. This makes n factorial. N times n minus 1 times n minus 2, all the way down to 3 times 2 times 1 makes n factorial. So we could say that the nth derivative of f of x is n factorial times c sub n x minus a to the n minus n. N minus n is 0, so that makes this the number 1, and it's gone. So we have a constant here, plus all these other terms. Now remember, the terms all have the form of some constant k times x minus a to some power out here. So keep that in mind, because what we're going to do is we're going to look at if we let x equal a. Let's go back up here. Remember, our center is a, centered at a. So if we go back up and let x equal a, then that doesn't really affect what we're doing here at all. But our nth derivative then is n factorial c sub n plus, remember we have some constant times x minus a. So when we put a in here, this becomes 0. And we have some other constant times x minus a to some other power up here. When we put a in here, it becomes 0. And that happens for all the other terms. So the nth derivative, this would be at a, not at x. At a. So the nth derivative of f at a equals n factorial times c sub n. So that leads us into the fact that we can now solve for c sub n. So c sub n equals the nth derivative of f at a all over n factorial. Now, a couple notes to remember is 0 factorial is always defined as number 1. That's true. And think about this. F prime of x means the first derivative, and f double prime of x means the second derivative, and it's read as such. So think about the fact of f of 0 of x means the original function, f of x, because there's no derivative yet. So this is our first note right here, and our second note is that if you're taking the 0 derivative, that's not even a thing, then we call it f of x because you're not taking a derivative yet. So that leads us into the theorem that we need to look at. And this is a theorem. And it says if f has a power series representation, f of x equals the series from n equals 0 to infinity of c sub n x minus a to the n. Power series representation, they actually say at a because it's centered at a. We know that x minus a is less than r, so that's our radius of convergence. Then the coefficients are given by c sub n equals, and it's that formula we developed, the nth derivative of f at a over n factorial. What does that mean for you for real? What this really means is not part of the theorem, but then we know that if we look at f of x, this means that we could rewrite it from this f of x up at the top. So we could rewrite it to be f of x equals the series from n equals 0 to infinity, the nth derivative of f at a over n factorial, so that takes the place of c sub n, times x minus a to the n power. So we don't write it with those big parentheses. We say the series from n equals 0 to infinity, the nth derivative of f at a over n factorial times x minus a to the nth power. So that helps us expand our series, and it looks like this. If we let n equal 0, then our first term is f, the 0 derivative of f at a. Well, that really means the function of a. As we talked about before, there's no derivative taken yet. Over 0 factorial, which is 1. And then we have x minus a to the 0 power, which is 1. So out of all of that, we just have f of a. So for the 0 term, let's just write f of a. So we have f of a plus, if we let n equal 1, we have the first derivative at a over 1 factorial, which is 1, so there's no need to write 1 factorial. Let's just write f prime of a times x minus a to the first plus the second derivative at a over 2 factorial, which is 2, times x minus a to the second. And then we have the third derivative of a over 3 factorial. 3 times 2 times 1 is 6, times x minus a to the third. Then remember, the fourth derivative is where that notation starts getting crazy. So we say the fourth derivative at a over 4 factorial. 4 times 3 times 2 times 1 is 24. X minus a to the fourth. And I think you've got the right idea, so we can stop now. So this equation right here, all of this, is the Taylor series. Do you understand where it comes from? So that's why we learned derivatives last time. We learned derivatives because we can use them to help us develop our Taylor series. So here we have our Taylor series. All of this represents our Taylor series. F of x equals this equation, and it can be expanded to look like this. So this is our Taylor series. You need to make a note of that. That's a very important series. Now, we might as well go ahead and talk about the Maclaurin series. So we're going to let f of x, let's let f of x equal the series from n equals 0 to infinity. We're still going to have the nth derivative, but here's the difference. Instead of looking at a, we're going to say at 0. So this series is centered at 0. We still have n factorial. The only thing that changes is that a becomes 0. So when you go back to this Taylor series, right here where you have a, it becomes a 0. And then here x minus a becomes x minus 0. So it's just x to the nth power. So the Maclaurin series is a special case of the Taylor series. There are lots of times where you learn, things are not as specific. So you have a polynomial that's very broad, and you have a monomial that's very specific. So in this case, you have a Taylor series that's very broad, and a Maclaurin is a special Taylor series. So this is called the Maclaurin series. Now the Maclaurin series can be expanded as well. It's going to look very similar to the one above. So if you let n equal 0, then you have not taken a derivative yet. So you have f of 0, and 0 factorial is 1. So you have f of 0, and x to the 0 is 1. So it's just f of 0 plus the first derivative at 0. I keep forgetting that it's over n factorial, which is 1. So it's just the first derivative at 0 times x to the first, plus the second derivative at 0 over 2 factorial, which is 2, x to the second, plus the third derivative at 0 over 3 factorial, which is 6, x to the third. And you can see the pattern happening. So this is the Maclaurin series. So you're going to either use the Taylor series if you're centered around A, or the Maclaurin series if the center is 0. And here's the difference. X to the n means Maclaurin series. X minus something to the n or plus something to the n represents the Taylor series. So that's the difference between the two. Let's look at an example. One note, let's go back real quick. One note to make is that the book says that if we have f and it can be represented as a power series about a, so right here, if we can write our function as a power series about a back here, then the function usually can be represented by a Taylor series. That's not true for all of them, but that's very often true. So now let's look at an example. Okay, this example says, find the Maclaurin series of the function f of x equals e to the x and its radius of convergence. Now, it says Maclaurin series here, but it could have said Taylor series, where a equals 0. So you need to know that the Maclaurin series is the Taylor series where a equals 0. So the way we start this problem is, let's go back to, let's not go back, let's make a note. For our Maclaurin series, we say f of x equals the series from n equals 0 to infinity, the nth derivative of f at 0 over n factorial x to the n. Now the good news is, no matter whether we're talking about a Taylor series or Maclaurin series, this is a constant. It doesn't change. This doesn't change. This is the part you have to figure out. We know that a equals 0, so that x to the n stays. This n factorial is not dependent at all on our series. So the only thing that has the possibility of changing is the box. And notice it's the nth derivative. So let's look at the nth derivative every time. You need to do several derivatives, like at least 4, so you can develop a pattern. And then we're going to do the derivative at 0 so we can figure out what to put in place of this box. So let's start with f of x equals e to the x. So the first derivative is e to the x. Nice, easy problem. And the second derivative is e to the x. And the third derivative is e to the x. Don't be lazy. And the fourth derivative is e to the x. So we can say with confidence the nth derivative is e to the x. But we don't want to just find them at x. We want to go back and find them at whatever a value we're given. But we know our a value is 0 because this is the Maclaurin series. So we say e to the 0 is 1. The first derivative at 0 is 1. The second derivative at 0 is 1. The third derivative at 0 is 1. And the fourth derivative of 0 is 1. At 0 is 1. So it's all about patterns. Once you can develop the pattern, show enough math to show that you thought about it, the nth derivative at 0 is 1. So that means for this specific problem, we say the series from n equals 0 to infinity, our nth derivative at 0 is the number 1 over n factorial x to the n. And there's our Maclaurin series. Now it asks us to do the radius of convergence. So keep that in mind and let's look at the ratio test. Now we move into the test that we looked at before. So let's do the ratio test. So it says the limit as n approaches infinity. And we have n plus a sub n plus 1. So we have 1 over n plus 1 factorial times x to the n plus 1 over 1 over n factorial x to the n. This is the limit as n approaches infinity. The numerator is 1 over, let's call it n plus 1 times n factorial. And on top of that, we have x to the n plus 1. So that's x to the n times x to the first. That gives me x to the n plus 1. And then we have n factorial over x to the n here. Now what's really nice is our x to the n's cancel, and our n factorials cancel. So we have the limit as n approaches infinity of, in the numerator we have x, and in the denominator we have n plus 1. So when we put in infinity, this means we have x over infinity, which equals 0 for all x. Now remember that was one of our cases, so the radius of convergence is infinity. What that means is our interval of convergence is negative infinity to infinity. That means that this series is convergent everywhere because the domain tells us where we're convergent. So this is our Maclaurin series, and our radius of convergence is infinity. Let me bring that up. And that's what we were asked to find. So it's not that bad for most of the time. For some of the time. You just need to do enough derivatives right here that you can find it. So you need to know what the pattern should look like. So know the pattern. The theorem, the formula, let's call it the formula. Know the formula. And then find lots of derivatives. Find enough derivatives to establish a pattern. Find the derivatives at A to determine the pattern. Set up the series. And then find the radius or interval of convergence. Remember, your interval of convergence is the only thing that matters because that's where our series converges, so that's where the domain is important. I think we have time for one more. I think we should go back real quick. The correct way to write your answer is to say that f of x equals e of x. E to the x can be represented by and we have the series from n equals 0 to infinity of 1 over n factorial x to the n with a radius of infinity because it works for all x values. While we're at this, let's talk about what this really means. So f of x equals e to the x can be written as let's let n equal 0. So we have x to the 0, which is 1 over 0 factorial, which is 1. And then we have x over 1 factorial, which is 1. And we have x squared over 2 factorial, plus x to the 3rd over 3 factorial, plus x to the 4th over 4 factorial. So what that means is if I find many of these terms and add them together, I can find f of e to some, I can find f of x equals e to some power. So let's say f of 3, this means we do x to the 3rd equals 1 plus 3 plus 3 squared over 2 factorial plus 3 to the 3rd over 3 factorial plus 3 to the 4th over 4 factorial. Now if you do those calculations and add them up, you'll find a very close approximation of x to the 3rd. Because it can be represented as such, then it works. If you let f of 1 equal e to the 1st, then you would let x equal 1. So we say 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and so forth. What's interesting is in 1748, interesting year, Leonhard Euler, his name is spelled like Euler, Leonhard Euler use this equation to find the correct value of e to 23 digits. Before calculators, 23 digits. In 2010, Shigeru Kondo used the same equation to compute e to more than 1 trillion decimal places. So Euler was cutting edge. I think we have time for an example. The problem says f of x equals 1 minus x quantity to the minus 2. And it says to find the Maclaurin series using what we've already talked about. So we start with the fact that we know that we need to find derivatives. So we find the first derivative to be negative 2 times 1 minus x to the negative 3 times negative 1. So this is 2 times 1 minus x to the minus 3. And our second derivative would be 2 times negative 3 is negative 6 times 1 minus x to the minus 4 times negative 1, which makes 6 times 1 minus x to the minus 4. And our third derivative is 6 times negative 4 is negative 24, 1 minus x to the negative 5 times negative 1, which makes 24 times 1 minus x to the minus 5. For the sake of time, I'm going to skip the first parentheses and say negative 5 times 24 is negative 120, and have 1 minus x to the minus 6, and this becomes a plus. Now, it's a Maclaurin series, so that means we're looking at f of 0. So f of 0, in this case, would be 1 over 1, which is 1. And then f prime of 0 would be 2 over 1, which is 2. And the second derivative at 0 is 6 over 1, which is 6. And the third derivative would be 24. And the fourth derivative at 0 would be 120. So remember our Maclaurin series says the sum from n equals 0 to infinity, f nth derivative of 0 over n factorial times x to the n. So that means 1 minus x to the negative 2 equals, the first one is f of 0, and then we have the first derivative at 0 times x, because 1 factorial is 1, and the second derivative at 0 over 2 factorial times x squared, plus the third derivative of 0 over 3 factorial times x to the third, and so forth. So looking at it term by term, we need to go back. So we have 1 plus 2x plus the second derivative is 6, and 2 factorial is 2, x squared. The third derivative is 24. 3 factorial is 6, x to the third. The fourth derivative is 120. 4 factorial is 24, x to the fourth, and so forth. So let's simplify. We have 1 plus 2x plus 3x squared plus 4x to the third plus 5x to the fourth plus, I think we can see a pattern here. So let's say the series from n equals 0 to infinity. We have n plus 1 because it starts 1 higher, x to the n. Notice x to the 0 and then times 1. So that kind of gives it to us. This is our representation of our function. So we're going to use the ratio test. And I'm running out of time, so I'm going to write some steps and then talk through them. So we have the limit as n approaches infinity of n plus 2, x to the n plus 1, over n plus 1, x to the n. So that's the limit as n approaches infinity. So we have using L'Hopital's rule, we find the following. So this gives us the absolute value of x, and we know to converge it has to be less than 1. So our radius of convergence is 1. Thank you.